In our earlier few classes, we have already designed a full adder by using minimum number of NAND gates, full adder by using two half adders and by using NOR gates, and also full adder by using minimum number of NOR gates. In today's class, we will be designing a full subtractor by using minimum number of NAND gates. So let's get started. First, we will start with half subtractor. We know the half subtractor is a combinational circuit which performs arithmetic subtraction of two binary digits. It has like half adder, it has two inputs and two outputs, and this time the outputs are called difference and borrow. This is the block diagram representation of a half subtractor where A and B are the inputs. Difference means D, and borrow, which is represented by B. These are two outputs. These are the truth table for a half subtractor that we have already seen in one of our earlier classes. These are the logical expressions for difference and borrow. So for difference, what we can see is it is same as half adder. So that is XOR operation between the two inputs A and B. And for borrow, it's slightly different, where in case of half adder, the carry was only AB and operation between AB. And in case of borrow, for a half subtractor, this is A complement B or A bar B. Now this is the logical circuit. This will give us A complement, and the output of this AND gate will be A complement B. And output of these two inputs XOR gate will be simple A XOR B. Now full subtractor is again a combinational circuit which performs arithmetic subtraction of three binary digits. That means in this case we will have three inputs and again two outputs, difference and borrow. And the third input of full subtractor could be the borrow of the previous stage or of the previous subtractor. This is the design of a full subtractor by using two half subtractors. So for this half subtractor, we have two inputs X and Y, and accordingly we will be getting the outputs, and then output of the difference of the first stage half subtractor or first half subtractor has been taken as one of the inputs of the second stage or the second half subtractor, and the second input of that second half subtractor is BIN, and the complete connection or diagram will be like this, where this is the difference. So difference of the second half subtractor will be taken as the final difference of the full subtractor. This design we have already seen in case of full adder by using two half adders, and the output of this OR gate will be the borrow of the or final borrow of that full subtractor. Now these are the logical expressions for difference and borrow that we already know, and this is the truth table for a full subtractor. So we have used here three inputs X, Y and BIN, and because of three inputs there are two Qs, so 8 combinations, and these are the difference corresponding to each combination of X, Y and BIN, and similarly these are the B borrow output corresponding to each combination. And before we implement a full subtractor by using minimum number of NAND gates or NOR gates, whatever, we should have a good knowledge of this truth table, how a full subtractor works. And this is the circuit diagram for a full subtractor, where we can see X, Y, BIN. These are the three inputs, and this output of this AND gate will be X bar Y, and output of this AND gate is again X bar BIN or X complement BIN, and output of this AND gate will be, here we have Y and here we have BIN, so this will be Y and BIN, and difference will be, here directly we have used a 3 input XOR gate just to represent the difference of full subtractor, and borrow will follow this expression, where this is the output of this OR gate and inputs of that OR gate are the outputs of their corresponding AND gate. Now we will go to the design of a XOR gate by using NAND gate, and this design we have already seen in case of implementation of full adder by using NAND gates. This simplification we are already aware of. Now this is A, so output of this NAND gate will be AB complement, and for this NAND gate, this output we are taking as one of the inputs, and directly A we are taking as the second input. So again this will follow the operation of NAND gate, and accordingly this will be the output, And if we simplify further, then by using De Morgan's law, this will be A and this is AB complement. So it will be A complement plus B complement, and then we have whole complement. A complement will give us 0. So finally it will be A and then B complement, and then we have another complement on that. And similarly, if we simplify the output of this NAND gate, where input, one of the inputs is the output of this NAND gate AB complement, and the second input is B, directly we are using here. So if we simplify further, then it will be B, and again if we apply De Morgan's law on this, then it will be A complement plus B complement and then whole complement. So here B and B complement will give us 0. So final term that we will have in this expression is B A complement or A complement B and then whole complement. And we have to remember these two expressions when we will be implementing full subtractor by using XOR gate. Now we will, in the first stage, we will use the same circuit that we have used to implement a XOR gate. Now here we have two inputs A and B. So what we have seen there, that the output of this NAND gate will be what? This will be A B complement and then whole complement, and the output of this NAND gate will be A complement B and then whole complement, right? And output of this NAND gate is what? This will be A XOR B. And what is the difference for a half subtractor? That is A XOR B if the inputs are AB, and for borrow, that is A complement and B. That means we have already obtained the difference of a half subtractor. Now we have to see how we can obtain borrow output of a half subtractor. And what we can see here, that we already have A complement B and then whole complement. So by using NAND gates, if we want to obtain, then this output, if that passes through another NAND gate, then what we will get? A complement B, already we have one complement, and on top of that we will have another complement. So those two complements will cancel each other. So here we will have A complement B. Here this 2B, if it confuses you, then what you can do is, instead of A, you can take the input as X, and instead of B, you can take that as Y. So in place of A complement B, we will get X complement Y. So as you feel comfortable and convenient, you can use as inputs. But here our aim is to design the full subtractor by using NAND. This is the design that I have shown you for your knowledge, that how you can design a half subtractor by using NAND gates. So for designing a half subtractor, how many NAND gates we need? 5. Now to design the full subtractor, we will repeat the same circuit in the second stage. So again we will have this circuit where we will have 4 NAND gates. Now what we will do, we will take the output of the first stage as one of the inputs of the second stage. So input of this NAND gate will be A XOR B, and the second input of the second stage will be the third input of our full subtractor, which is B suffix in, BIN. So as per the working principle of this circuit, we have seen that the output is A XOR B when the inputs are AB. So when the inputs are A XOR B and BIN, the output will be what? It will be first input, which is A XOR B, and then with that XOR with the second input, which is BIN. So what we can see here, we have already obtained the difference of the full subtractor. Now we are yet to get the borrow output for this full subtractor circuit, which is right. To get that, what we will do is, we will take output of this NAND gate and output of this NAND gate, and those two will be used as inputs of another NAND gate, and output of that NAND gate will be this. So one input of this NAND gate is already, we know this is A bar B and then whole bar. And what will be the other input of this NAND gate? This will be, as per this rule, A complement B bar. So when A, B were inputs for this circuit. Now one input for this circuit is itself is A XOR B. So it will be A XOR B and then complement of that. So with that, we will, the second input of this circuit, which is BIN, that will be in AND operation, and then we will have this whole complement. So when this two will be taken as inputs of this NAND gate, the output of that NAND gate will be this. So that we will also prove in this class. So the output of that final NAND gate was, now this thing we will simplify. So again, this thing, this A complement B and then this complement, whole complement, if we take that as one input X, and A XOR B complement with that BIN and their whole complement, if we take that as another input Y, so XY complement, so by De Morgan's law it will be X complement plus Y complement. So how it will be written? It will be A complement B, then already we had one complement, and by De Morgan's law there will be another complement, then we will have plus, then A XOR B and then complement, with that we had BIN, and then we had one complement, and because of the De Morgan's law we will have another complement on that. So in both the terms these two complements will cancel each other. So finally here in the first term we will have A complement B, and in the second term we will have A XOR B, and then we will have this complement and with that BIN. So if we simplify further, it will be A complement B, then plus A XOR B and then complement. That means this is A XNOR B. So A XNOR B means it will be AB plus A complement B complement, and then we will have BIN with that. So now we can combine the third and fourth term. So second term will be BIN, and from here the common inputs are A complement BIN. So if we take that as common, then within bracket it will be B plus B bar or B complement. So finally it will be A bar B, and from here we will have A bar BIN and plus B BIN. So what is that? This is borrow output of a full subtractor. That means we can say that the output of this NAND gate will be the borrow output of a full subtractor. So this is the way how we can design or we can implement a full subtractor by using minimum number of NAND gates. And how many NAND gates we have used here? Total 9 NAND gates. So to design a half subtractor we need 5 NAND gates, and to design a full subtractor we need 9 NAND gates in total. So I hope this class was helpful and meaningful for you. With that hope I end today's class. Thank you.